Here's a 3 by 4 matrix A. Row 1 is 1, 2, 3, 1. Row 2 is 1, 1, 2, 1. And row 3 is 1, 2, 3, 1. From a single row reduction, we'll extract 4 bases, one for each fundamental subspace, but there's a trap. One of those bases cannot come from the reduced form. It must come from the original matrix. Let's start with the row reduction, the engine behind everything. Take matrix A, we will row reduce it step by step to find the reduced row echelon form. First, subtract row 1 from row 2. Row 2 becomes 0, -1, -1, 0. Next, subtract row 1 from row 3. Since rows 1 and 3 were identical, row 3 becomes all zeros. Now, multiply row 2 by -1 to get 0, 1, 1, 0. Finally, subtract 2 times row 2 from row 1. Row 1 becomes 1, 0, 1, 1. This gives us the reduced row echelon form R. Row 1 is 1, 0, 1, 1. Row 2 is 0, 1, 1, 0. Row 3 is all zeros. The leading ones appear in columns 1 and 2. A pivot column is one that contains a leading one in the reduced form. Columns 3 and 4 are free columns, meaning they contain no pivots. The rank R equals 2. The column space of A has dimension equal to the rank, which is 2. The pivot positions tell us which columns of A to select. Columns 1 and 2 are the pivot columns. Here's the critical step. Go back to the original matrix A and extract those columns. Column 1 of A is 1, 1, 1. Column 2 of A is 2, 1, 2. These two vectors form the basis for the column space. We take them from A, not from R. Now look at the right side. If we mistakenly took the pivot columns from the reduced matrix R, we'd get the vectors 1, 0, 0 and 0, 1, 0. Those are completely different vectors, and they do not give the correct basis for the column space of A. The column space has dimension R equals 2, but the actual basis vectors must come from the original matrix. We'll see exactly why that matters in a moment. We found the column space. Next, we compute the null space, that's all vectors x, where Rx equals 0. Writing out the reduced matrix R, the system Rx equals 0 gives us two equations, x1 plus x3 plus x4 equals 0, and x2 plus x3 equals 0. The pivot columns are columns 1 and 2, so the free variables correspond to the non-pivot columns. Here, x3 and x4. A free variable is any variable tied to a non-pivot column. For the first special solution, we set x3 equals 1 and x4 equals 0, then back substitute. From row 2, x2 plus x3 equals 0, so x2 equals -1. From row 1, x1 plus x3 plus x4 equals 0, so x1 equals -1. That gives us s1 equals -1, -1, 1, 0. For the second special solution, set x3 equals 0 and x4 equals 1. Row 2 gives x2 equals 0. Row 1 gives x1 plus 0 plus 1 equals 0, so x1 equals -1. So s2 equals -1, 0, 0, 1. The null space basis is the set containing s1 and s2, and the dimension is n minus r, which is 4 minus 2 equals 2. 2 subspaces down, 2 to go. For the row space, we read the basis directly from R. The reduced row echelon form R has rows 1, 0, 1, 1 in the first row, 0, 1, 1, 0 in the second row, and a 0, 0, 0, 0 in the third row. The non-zero rows of R form the basis for the row space, so our basis vectors are 1, 0, 1, 1, and 0, 1, 1, 0. Notice the identity pattern in the pivot positions. Columns 1 and 2 of the first two rows form a 2 by 2 identity block, and this is a hallmark of reduced row echelon form. The dimension of the row space equals R, which equals 2. These vectors live in 4-dimensional real space, the same space as each row of A. Here's why reading the row space from R is valid. Every row operation replaces a row with a linear combination of existing rows, so the new rows stay in the span of the old rows. And the process is reversible because the elimination matrix E is invertible, which means old rows are recoverable from new ones. Therefore, the spans are identical. Row operations preserve the row space completely. Row operations preserve the row space. They do not preserve the column space. Here is the proof. Consider the column space of A. Column 1 of A is the vector 1, 1, 1, which is clearly in the column space of A. Now look at the column space of RR equals the matrix with rows 1, 0, 1, 1, then 0, 1, 1, 0, then 0, 0, 0, 0. Let's list out all 4 columns of R. Column 1 is 1, 0, 0. Column 2 is 0, 1, 0. Column 3 is 1, 1, 0. And column 4 is 1, 0, 0. Notice something important. Every single column of R has a 0 in the third entry. So any linear combination, C1 times 1, 0, 0, plus C2 times 0, 1, 0, plus C3 times 1, 1, 0, plus C4 times 1, 0, 0, always gives a result of the form star star 0. The third component is always 0, no matter what scalars you choose. Therefore, the vector 1, 1, 1 lives in the column space of A, but it does not live in the column space of R. The 2 column spaces are different, and this is exactly why when we find a basis for the column space, we must take the pivot columns from the original matrix A, never from our row operations, reshuffle the entries within each column, and that changes the column space. The fourth and final subspace is the left null space, the null space of A transpose. Vectors Y in this space satisfy Y transpose times A equals the 0 row. To find it, we augment A with the identity matrix, form the 3 by 7 matrix, a vertical bar I. We then apply the same row operations we used before, but now we track the effect on the right-hand side too. Step 1, replace row 2 with row 2 minus row 1. The right side of row 2 becomes negative 1, 1, 0. Step 2, replace row 3 with row 3 minus row 1. The right side of row 3 becomes negative 1, 0, 1. Step 3, replace row 2 with negative row 2. The right side of row 2 becomes 1, negative 1, 0. Step 4, replace row 1 with row 1 minus 2 times row 2. The right side of row 1 becomes negative 1, 2, 0. The final result is R on the left and the elimination matrix E on the right, satisfying E times A equals R. E equals row 1 is negative 1, 2, 0. Row 2 is 1, negative 1, 0. Row 3 is negative 1, 0, 1. Now, the third row of R is all zeros. The matching third row of E is negative 1, 0, 1. That vector forms our left null space basis. Let's check it. Negative 1 times row 1 of A plus 0 times row 2 plus 1 times row 3. That's negative 1 times 1, 2, 3, 1 plus 1 times 1, 2, 3, 1, which gives 0, 0, 0, 0. And this makes perfect sense. Rows 1 and 3 of A are identical, so their difference vanishes. The dimension is M minus R, which equals 3 minus 2 equals 1. We now have all 4 fundamental subspaces from one computation. Let's organize them in a summary table. The column space of A lives in R3. Its basis vectors are 1, 1, 1, and 2, 1, 2, taken from the pivot columns of A. Its dimension is R equals 2. The null space of A lives in R4. Its basis vectors are negative 1, negative 1, 1, 0, and negative 1, 0, 0, 1, found from the special solutions of R. Its dimension is n minus R equals 2. The row space, also called the column space of A transpose, lives in R4. Its basis vectors are 1, 0, 1, 1, and 0, 1, 1, 0. Read from the non-zero rows of R. Its dimension is R equals 2. The left null space, the null space of A transpose, lives in R3. Its basis vector is negative 1, 0, 1, obtained from the 0 row of the elimination matrix E. Its dimension is m minus R equals 1. Now let's check the dimensions. The row space dimension plus the null space dimension gives 2 plus 2 equals 4. which is n. The column space dimension plus the left null space dimension gives 2 plus 1 equals 3, which is m. This is the fundamental theorem of linear algebra in action. A single matrix encodes 4 subspaces organized in 2 pairs. Row reduction unlocks all of them. Read the row space from R, the null space from R, the column space from A, and the left null space from E. For the row space and null space, which live in Rn, their dimensions are R and n minus R. For the column space and the left null space, which live in Rm, their dimensions are R and m minus R. 3 matrices, A, R, and E, and 1 number, the rank R, tie every dimension together. The full pipeline is A leads to R leads to E. 1 computation reveals 4 subspaces. Master this, and you've mastered the structural skeleton of any linear system.